This is the Module 12.3 SAS video. So to start out with, we want to make sure that we've got all the files that we need in our folder. So here's my folder. Notice that I've got the 12.3 SAS Notes, I've got the Module 12 SAS Code, and then I've also got my data set and I've got my code book. So we're going to need all of these different things. So let's start by looking at the 12.3 SAS Notes. So in this note set, we're going to look at 4 different types of confidence intervals, and we're going to look at how they could relate to the BRFSS data set that you've been working with. So we're going to start out by looking how we can use SAS to calculate a confidence interval for a single mean here. So a research question that you might be interested in is, what is the mean BMI for people living in Kentucky during 2018? And of course you're interested for your state. Well, you can use a confidence interval to help us with this. So let's open up our SAS code. So here I've got my SAS code down here at the bottom. And remember, the first thing that we always have to do is read in our data set. So that's going to be the first thing that I do. Now, in order to do this, I first need to change my working directory so SAS knows, where to find the files I'm working with. So going to my folder, I'm going to copy this part, open SAS back up, and I'm going to make sure I change everything except for the file name. All right, and I'm going to run this. Alright, so SAS wasn't happy with that. Let me go back and see what I did wrong here. So notice my file name. Need to change that to BRFSS. Let's try this again. Alright, and this time SAS was happy, so we're good to go. Alright, so we're going to start out by finding a confidence interval for a single mean. So we're going to do this for the BMI variable. So as always, the first thing we want to do is look up this variable in our code book. So we're going to pull up the code book here. Remember, if you hit Control F, that'll bring up a search box so we can search for our variable, and here it is. So looking at this variable, notice it takes the values 1 up to 9,999. This is a quantitative variable. They tell us that they calculated this variable using the weight and the height variables that people have responded to, so this is a calculated variable. And notice also they tell us that it has 2 implied decimal places, and that'll be important here in a little bit. And then finally, anybody that said don't know, refused, or missing to either the weight or the height, they've already changed all of that over to missing. So for this particular variable, we don't have to worry about don't know or refuse, because all of that has already been changed over to missing data. All right. So going back to our SAS code here. The first thing we're going to do is we're going to look at the data distribution for this variable. And remember, the reason that we need to do this is we're trying to make sure that the inferential procedures that we use are appropriate, so we need to check our assumptions. So I'm going to run this line of code right here. And notice here is my histogram. Now, it's not particularly pretty, but the idea is I just want to get a quick glance to see, hey, does this thing look normal or not? Because if my population is normal, then I know that it's valid for me to use the confidence interval. And one way for me to assess if my population is normal is by looking at the data distribution. Because if the sample data looks reasonably normal, since this is a random sample, it's reasonable to think that the population data is also normal. Now, looking at this data distribution, it does have a slight right skew to it. I'm not overly concerned, but it does have a right skew to it. So the next thing that I want to check is the sample size requirement and make sure that I've met the sample size requirement for the central limit theorem. And so in order to do this, what I'm actually going to do is I'm going to go ahead and calculate the confidence interval, and in that calculation, it will tell me the sample size. So to calculate the confidence interval, we're going to use the proc mean statement that you've seen before. I'm going to call the variable that we're interested in, and notice that I've added some extra stuff up here, such as mean, standard deviation, n. So I'm going to get the mean, I'm going to get the standard deviation, n is going to give me the sample size, and I've also called this CLM. That's what's going to give me the confidence interval. So let's run this. All right, so here is my output. Notice n, which is my sample size, is 9,198. This is more than large enough for the central limit theorem to apply, so I'm safe to, create this confidence interval. I also get the lower and upper bounds for the confidence interval. Going back to the SAS code just quickly, notice one of the other things is the alpha equals 0.05. Remember, we want a 95% confidence interval. So SAS wants what is called the alpha, and that's equal to 1 minus the confidence level. So for example, if I wanted a 90% confidence interval, I would put 0.1 here. And then max decimal places, that's just controlling how many decimal places that SAS is going to produce in the output. So let's go back to our notes. Notice here, I've got that output copy and pasted, and it's these two pieces that give us the confidence interval. Now, we always want to make any note on our data, anything that needs to be noted. So in this case, the code book, we know that the values have 2 implied decimal places. So what does this mean? Well, BMI does not take values that are like 2,907. That's not a reasonable value for BMI. Really what these values are is 29.07 and 29.41. So in conclusion, we can say we are 95% confident that the true mean BMI for the state of Kentucky was between 29.08 and 29.41 in the year 2018. Note that an individual is considered overweight if BMI is greater than 25. Since all of the values in the interval are greater than 25, this suggests that on average, Kentuckians were overweight in the year 2018. And so an important thing to notice here is that I've said on average. We're trying to learn about the population mean here, or an average. So any conclusions that we make have to be about Kentuckians on average, not individual Kentuckians. All right, next we're going to look at a confidence interval for a single proportion. So a question we might be interested in is, what is the proportion of people living in Kentucky during the year 2018 who received a flu vaccine? And that should say, what proportion of people living in Kentucky during the year 2018 received a flu vaccine? So let's use a confidence interval to help us with this. So again, we've got some SAS code here. The variable that we are going to look at for this example is the flu shot 6 variable. So let's go and look at that variable in our code book. So going to our code book. All right. Here's information about flu shot 6. So we can see there are 4 possible values that someone could reply with. There are the yeses, the nos, the don't knows, and the refuses. So looking at the code here, let's first make a table of the flu shot 6 variable. So here's our frequency table. We can see there are 2,612 people who said yes, 3,765 people that said no. We had 16 who didn't know, and we had nobody that refused to answer. So next, to calculate the confidence interval, we're going to use the proc-freq statement that we have seen before, and we're going to add in this slash binomial after the table statement. So let's run this. All right, this is going to produce quite a bit of output here. We get our frequency table, and notice it's going to have the binomial proportion here for flu shot equal to 1. So it's going to give us the proportion for the first one, which is the one that we want here. So flu shot equal to 1. And notice here are our different confidence limits. So let's go back to our code here, and then we'll go to our notes. So notice here are the different pieces for the confidence interval. So one thing to notice here, what SAS is doing is it's comparing flu shot equal to 1, the first one, compared to all of the other groupings. So in other words, it's looking at the proportion of no's, don't knows, or refused, and using that as the complement of yes. So you want to be careful here when you report what the percentage of yeses, because this is not the proportion of yeses compared just to the no's. This is the proportion of yes compared to everything else. So in conclusion, we can say we are 95% confident that the true proportion of people in the state of Kentucky receiving a flu vaccine in the year 2018 was between 39.65% and 42.1%. Since all of the values in the interval are less than 50, this suggests that less than half of Kentuckians received a flu vaccine in the year 2018. And we may want to be even more specific here, because remember that the survey specifically looks at adult responses unless your individual state collected data on children. Right, next we're going to look at a difference in means. So a research question we might have is, what is the difference in the mean BMI for people living in Kentucky with good, better health compared to the mean BMI for people living in Kentucky with fair or poor health during the year 2018? And so again, we can use a confidence interval to help us with this. Alright, so the first thing that we're going to want to do is, again, look at our two different variables. We've already examined the BMI variable previously, so now let's go and look at the health variable. So the health variable is RFH LTH. So again, going to our code book. Notice that this variable takes the value 1 if the person is in good or better health, and fair if they are in, or 2 if they are in fair or poor health. And then the value 9 groups all of the don't knows, not sures, and the refuses together. So those are all grouped together. So the first thing we're going to do is we're going to use the proc univariate statement, and what we're going to do is we're going to calculate the BMI variable for each of those different health types. And again, this is similar to what you've seen before in previous code. So what we've got here is a bunch of output. We're going to look at all of the different potential values for health. So we've got health is 1, health is 2, and then health is 9. We're particularly interested in health is 1 and health is 2. So notice here we had 4,574 responses for the health is equal to 1. That's how many observations we have for BMI. That's more than large enough for the central limit theorem to apply. And then also for health is equal to 2, we had 1,613 observations for the BMI variable. So in this case, also the central limit theorem would apply. All right, when calculating the confidence interval for a difference in means, you need to decide if the population variances are equal or not. And the general rule of thumb to evaluate this is to look at the sample standard deviations, and if the largest sample standard deviation divided by the smallest is greater than 2, then you need to assume unequal variances. So there's two different ways that we could approach this confidence interval. So the first thing we're going to do, and this should say for the variable health, let me change that really quick here. We're going to remove those don't know, refused responses that we don't need. So what I've done here is I've started out with my original, or I'm going to make a data set called Kentucky 2018 BRFS. And the first thing I'm going to do is add my original data set to it. And then I'm going to create a new variable called health. I'm going to set it equal to the old variable. And if my original variable is greater than 2, in other words, remember 9 was don't know, refuse, don't know, we really only care about the 1s and 2s, then I set it equal to missing. So again, we've done steps like this very similar to what we've done before. So we're going to run that line of code, just double check my log there, and now we're going to calculate our confidence interval. So we're going to run the proc.t t-test function. I'm going to give it my data set. The class health is going to define the grouping variable, so that's going to be health in this case because that defines my two different groups. And then the variable I'm interested in is the BMI 5. All right, so again, we get a lot of output here. And so we're going to look at what some of these different outputs are. So first of all, we've got health 1 and health 2. Again, we've got those two different sample sizes, which meet the central limit theorem requirements. And notice we've got their standard deviations. If you were to take the ratio of these two standard deviations, in other words, if you took the 767.6 divided by the 617.9, you would see that that is less than 2. So it would be safe in this particular case to assume that the population standard deviations are equal to one another based on what you see in the two different samples. Now, a more conservative method is to assume that they are not equal, which would also be valid to do in this particular case. Notice down here we have two different confidence intervals that they've given us. One is the pooled method and one is the Satterthwaite. So if we go back and look at our output, notice here in the notes where I've copied the output over, I have highlighted the pooled one. So the pooled confidence interval assumes that the population standard deviations are equal. Since that ratio was less than 2, I went with that option in this case. On the other hand, I could have said, hey, I'm not comfortable making that assumption, so I'm going to go with the assumption that the population standard deviations are not equal to one another, and in which case I would have used this interval right here. Notice that the second interval is a little bit wider than the first one. So it's wider because it's accounting for that additional uncertainty in the population standard deviations not being equal to one another. It's a more conservative approach and will usually result in a larger confidence interval. So just like before, I'm going to make some notes about my data. From the code book, we know that the values have those two implied decimal places, and my analysis here assumes equal standard deviations. If you chose to go the other route and use the unequal standard deviation confidence interval, you would want to report that here. And then finally, in conclusion, we are 95% confident that the true mean BMI for people living in Kentucky with good, better health is between 2.58 and 1.83 less than the mean BMI for people living in Kentucky with fair, poor health. And notice the reason I have less here is because these values are negative. So what this is telling me is since that interval does not contain 0, it's not plausible that the two means are equal. And in fact, what we're finding out here is those with good and better health have a lower BMI on average than those with the fair, poor health on average. All right, our last example we're going to look at is a confidence interval for a difference in proportions. And so our question here is, what is the difference in the proportion of people living in Kentucky with good, better health who received the flu vaccine compared to the proportion of people living in Kentucky with fair, poor health who received the flu vaccine during the year 2018? So again, going to our SAS code. All right, so the first thing we're going to do is look at a contingency table. And so we're going to compare our two different variables of interest. They are the flu shot and the health variable, both of which we have already looked at in the code book. So running these, we get our contingency table. Notice that we are really interested in flu shot 1, flu shot 2, and health 1 and 2. Notice that all of the counts in these four boxes, they are large enough for the central limit theorem to apply, so we are safe to go ahead and calculate the confidence interval. All right, so in order to calculate the difference in proportions, what we need to do is we need to translate this data into a table that only has what we were interested in. So in other words, the flu shot 1 and 2 and the good health 1 and 2. Now what we're going to do is we are going to group together the knows, don't knows, and refused into one group. In other words, what we're saying is we're interested in the proportion of people who replied yes, and then the complement to that is going to be everyone else. Very similar to what we did when we looked at one proportion, except now we're going to do it for our two different health groups. So what I'm going to do is I'm going to define a new data set called flu data to store this in. And I'm going to input three different pieces of information. One, whether they got the flu shot or they did something else, what type of health they have, and then the number of people that fall into the categories. And so what I mean by the categories is, again, if we go back to our frequency table, so again, looking at my frequency table, remember there were really only 4 cells of this frequency table I'm interested in. This cell, this cell, this cell, and this cell. So that's what I'm summarizing here. So the first line of code that I'm going to enter is I want to find the number of people that got their flu shot and were in the good, better health. And so looking at my table, notice there was 1,876 people who fell in that category. So the count is 1,876. Then, for the people in good health, I want to get all of the other responses grouped together. So for those in the good health, which is this column right here, here are all of the no's, which is 2,829. But remember what we're going to do is we're going to combine the no's, the don't knows, and the refuses together. So for those in good health, it's not just that I want this one, I'm also going to tack on that 11 to incorporate those other people. And if I had anyone that had refused, I would also put that number. So notice that is going to give me my count, the 11 plus the 2,829. That's going to give me my 2,840. Next, for those in the poor or fair health category, we're going to do something similar. I had 732 of them who got the flu shot. So here, my yes flu shot, poor health is 732. And then everything other than yes for the flu shot for those in poor health is 931. So once we've condensed this table that we had, that contingency table, into this new data set, now we can get our confidence interval for a difference in proportion. So we do that by running the following. We're going to use the proc freq statement that we've done before, but now I'm going to add on this /risk diff. So for the single proportion, we added on that binomial statement. Now we add on this risk diff statement. We're going to run this. Oh, need to run my new data set. And you'll see it's going to give me some different pieces of information here. It actually gives me 2 sets of confidence intervals, so let's see which one we need to use. Remember that I'm interested in the difference between those in my good health who got the flu shot versus those in my bad health who got the flu shot. So getting the flu shot is what I'm interested in. So if we look up here, notice that flu yes is really the column 2. So down here, I want to look at the column 2 risk estimates. And notice it gives me a confidence interval for the difference. So this piece right here is the confidence interval that I want. So going back to my notes, notice here is that column 2 risk estimates, and here is my confidence interval. So again, we want to note here that the proportion of those responding no, don't know, or refused, we use that to be the complement of yes. And in our conclusion, we are 95% confident that the true proportion of people living, people living in Kentucky with good, better health who received the flu vaccine is between 1 to 7% less than the proportion of people living in Kentucky with fair poor health who received the flu vaccine during the year 2018. And again, we've got the word less here because the interval was negative. So note that since the interval does not contain 0, it's plausible that the two proportions are not equal to one another. And notice what we're finding out here is those that are in the good or better health, they are getting the flu vaccine at a lower proportion than those in the poor health. So this concludes the Module 12.3 SAS video. Of course, if you have any questions when you go to run your code, or if there's something you want to do that wasn't covered here, please let me know and I am more than happy to help.